So in this video we're going to talk about how to differentiate functions in this form. So we have a times x to the n. So where a is a constant and n is the exponent that x is being raised to. So the derivative of any function in this form is you just take this exponent down into the front as a coefficient and then subtract 1 from the exponent. And you just kind of ignore the constant while you're differentiating. So the derivative is going to be a times n times x to the n minus 1 power. And if you think about the functions that you already know how to differentiate, x squared, x, and just a constant, then it's consistent because we know with x squared, you take the 2 down and subtract 1 from the power. So you get 2 times x to the 1, or just 2x. And then if you have a function y equals x, that's x to the first power. So if you take 1 down and then subtract 1 from the power, you have 1 times x to the 0, which is just 1. And if you have a constant, say you have a constant c, that's the same thing as saying c times x to the 0 power. So when you bring the 0 down, everything becomes 0. So to see why the power rule works, we can apply the definition of a derivative. So say we want to find the derivative of this function y when x is equal to x0. So we find the two values. When x0, what is y0? And then when x is x0 plus delta x, what is the change in y? So it'll be y0 plus some change delta y. So then we can subtract these two to get delta y is equal to x0 plus delta x all to the n power minus x0 to the n. And now to deal with this expression over here, we can use the binomial theorem. Remember, the binomial theorem is something that we can use to expand expressions in this form. So we have a plus b, which is any two quantities, raised to the n power, where n is a positive integer. So the expansion will look something like this. And the actual numbers in the expansion aren't really important. So the important part is this. So here a is x0 and b is delta x. So if you write the first few terms, the first term will be x0 to the n power, and then we'll have n times x0 to the n minus 1 times delta x. And so notice that for all of the terms after this one, since the power of b keeps going up, here is b squared, it keeps going until b to the n power. Every term after this one will have delta x to the some power. This one's delta x squared, then it will be delta x cubed, and so on until we have delta x to the n power. So all of these terms except this one, these two, have more than one delta x in them. So that's the important part. So when we expand this expression with the binomial theorem, notice that we can now subtract this x0 to the n power, and this x0 to the n power will cancel out. So we just have all the rest of these terms. And then when we divide by delta x, since this term is the only one with only one delta x, this is the only term after dividing by delta x which will not have a delta x left over. So then when we take the limit as delta x approaches 0, all these terms will also approach 0 and they will cancel out. So all we have is the limit as delta x approaches 0 of delta y over delta x, which is our derivative, is equal to this first term over here, n times x0 to the n minus 1. So technically this way of proving the power rule only works when n, the exponent, is a positive integer, because the binomial theorem only works for positive integer powers. But I'm just going to tell you right now, the power rule works for any number n. So you can go ahead and start using it, but know that this is not the way to prove it if n is not a positive integer. So of course, whenever you find a new derivative formula, you also find a new integral formula, because you just have to go backwards. So to find the derivative of x to the n, we took the exponent down to the front and subtracted 1 from the exponent. So that means if we want to go backwards, we start with dy dx equals ax to the n. Then we're going to raise the exponent by 1 first, and then divide by the new exponent. So the integral of ax to the n, we ignore the constant while we're integrating. So then we'll have a times x to the n plus 1 divided by n plus 1. And then don't forget the plus c at the end. And if you haven't seen this before, this is the notation for the indefinite integral, or anti-differentiation. And this dx over here is just part of the notation. It just means to integrate with respect to x. So we can look at a case of when the power is not a positive integer. So let's find the derivative of x to the 1/2 power, or the square root of x, and see if the power rule applies here as well, which I already said that it did, but let's see that it works. So say we want to find the derivative at x0, so then we find the values of y0 and then the y value when x is x0 plus delta x. And then we subtract them as usual to find delta y, and then divide by delta x. And then so before we can evaluate this limit, we're going to multiply by the conjugate of this expression up here. So the conjugate, remember, is just when you change this sign on this before the second term. So we're going to multiply the top and bottom of this right side by the square root of x0 plus delta x plus square root of x0. And once we do that, we find that these x0's here cancel out, and then once these are gone, we can cancel out these delta x's. So all we have is this expression over here. And this expression is much easier to evaluate the limit as delta x approaches 0. Because as delta x approaches 0, we just get rid of this term over here. And then we have just 2 of the square root of x0's. So we can combine them, and then we just have 1/2 x0 to the negative 1/2 power. And so it seems like the power rule works even when we have a fractional power, because we just took the power down to a coefficient and then subtracted 1 from the power. And also note that this derivative is a little interesting. So our original function y equals square root of x is defined at x equals 0, because square root of 0 is 0. But the derivative is not defined at x equals 0, because you can't divide by 0. And so this is the graph of the original function square root of x. And remembering that the derivative is the slope of the tangent line, you can see that as x approaches 0, the tangent line gets really, really steep. So the slope of the tangent line is going to be increasing, a lot, to infinity. So we can say that the limit as x approaches 0 of 1/2 square root of x is infinity. But, be careful, because the limit does not actually exist. A limit has to be a number, and infinity is not a number. So really all this expression doesn't mean that the limit is infinity. It just means that as we go x approaches 0 in this expression, the output is going to keep getting higher and higher without bound. So just this limit thing really just stands for this sentence. The limit does not exist. So let's do one example of differentiating and integrating each with the power rule. So we have 3x to the 7/2 power. So remember, we ignore the constant for now, and then we bring the power down to differentiate, and then subtract 1 from the power. So we just have 21 over 2 times x to the 5 over 2 power. So then let's integrate square root of 8x. So first we can split this expression up into square root of x times square root of x. Square root of 8 times square root of x. And x is, to the 1/2 power. So we can ignore the constant for now. And then we add 1 to the power, so it becomes 3/2, and then divide by the new power. So we divide by 3/2, which is the same thing as multiplying by 2/3. And then don't forget to add c at the end.